Ever wondered why apples fall from trees instead of floating away? Or why we're not flung off the earth as it spins around the sun? It's all about gravity. Have you ever been struck with intrigue, watching the simple act of a leaf tumbling from a tree or a stone rolling down a hill? It's these seemingly ordinary occurrences that have sparked human curiosity throughout the ages. What makes things fall? Why don't we drift off into space? The elusive answer to these questions is a fundamental force that governs our universe: gravity. Gravity, an unseen force, is the invisible strings that orchestrate the cosmic ballet. It pulls objects towards each other, and it's responsible for the mesmerizing dance of planets around stars, and the grand symphony of galaxies swirling together in the vast expanse of the cosmos. This force was first named and described by one of the greatest minds in history, Sir Isaac Newton, in the 17th century, but it doesn't stop there. The concept of gravity was further refined by another brilliant mind, Albert Einstein, in the early 20th century. His theory of general relativity gave us a new perspective on gravity. It's not just a force, but a result of the curvature of space-time caused by the presence of mass and energy. The more massive an object is, the stronger its gravitational pull. This is why the Earth has a stronger gravitational pull than the Moon, and why the Sun has a stronger gravitational pull than the Earth. Gravity is also the reason why things have weight. Weight is the force exerted on an object due to gravity, and it is proportional to the mass of the object. This is why objects weigh less on the Moon than they do on Earth, because the Moon has less mass and therefore less gravitational pull. So, gravity is the unseen force that holds our universe together. But how does it really work? To understand gravity, we first turn to Sir Isaac Newton, who tackled this question in the 17th century. Newton, a mathematician and physicist, proposed the law of universal gravitation. This law states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This might sound a tad complex, but let's break it down. Imagine two bodies in space, one being the Earth and the other our Moon. According to Newton, these two bodies attract each other due to gravity. The force of this attraction depends on two factors: the mass of the objects and the distance between them. The first part of Newton's law tells us that the larger the mass of the objects, the greater the force of attraction or gravity between them. That's why the Earth, which is significantly more massive than the Moon, has a stronger gravitational pull. The second part of the law revolves around distance. It tells us that the further apart the objects are, the weaker the gravitational pull between them. This is why, despite its massive size, the Sun's gravitational pull on us is not as strong as that of the Earth. Even though the Sun is much more massive than the Earth, it's also a staggering 93 million miles away. Newton's law of universal gravitation was a monumental breakthrough, as it allowed us to understand why the planets orbit the Sun, why the Moon orbits the Earth, and why we don't float off into space. It also paved the way for advancements in physics, astronomy, and various other fields. However, while Newton's law of gravity was groundbreaking, it wasn't the whole picture. It explained the what, but not the how. It didn't explain how gravity worked or why mass seemed to attract mass. For that, we needed a deeper understanding, a new perspective. Enter Albert Einstein. Albert Einstein revolutionized our understanding of gravity in the early 20th century with his theory of general relativity. With this groundbreaking theory, Einstein took us on a journey far beyond the realms of Newton's apple and into the depths of the cosmos. Imagine, if you will, space and time woven together into a four-dimensional fabric known as space-time. This is the stage upon which the universe dances. Now picture a heavy object placed on this fabric. Just as a bowling ball placed on a trampoline stretches the material and causes it to sag, so too does a massive object warp the space-time around it. This is what we perceive as gravity. In Einstein's universe, the Sun doesn't simply pull the Earth towards it like a cosmic string tied between them. Instead, the Sun distorts the space-time around it and the Earth moves along this curvature. It's like a marble rolling around the edge of a funnel, drawn inexorably towards the center, not because of a direct pull, but because of the shape of the funnel itself. This revolutionary idea, the curvature of space-time, is at the heart of general relativity. It's a concept that takes us beyond the idea of gravity as a simple force and introduces us to a universe where mass and energy can literally shape the cosmos around them. Einstein's theory also had some mind-boggling implications. For instance, It predicted the existence of black holes. These cosmic behemoths are regions of space where gravity is so strong, due to an extreme warping of space-time, that nothing, not even light, can escape their grasp. Einstein's theory gave us a new way to understand gravity. But this isn't just some abstract cosmic concept. It has real-world implications. For example, the GPS navigation systems we use every day need to take into account the effects of general relativity to keep us on the right path. So, what does this mean for us in practical terms? That's a journey we'll continue in the next scene. Gravity is more than just a concept in physics textbooks. It's a force that affects our lives in many ways every day. Let's start with something basic, yet fundamental: weight. When we step on a scale, the number that pops up is a result of gravity pulling us towards the Earth. The force of gravity is directly proportional to the mass of an object. That's why a feather weighs less than a bowling ball. But if you were to take that same feather and bowling ball to the moon, they'd both weigh less because the moon's gravitational pull is weaker than Earth's. Gravity also influences phenomena that we often take for granted. Consider rain, for instance. Gravity pulls raindrops towards the Earth, giving us the rain we need to grow our crops and fill our reservoirs. It also makes rivers flow, guiding them along the path of least resistance towards the sea. But the influence of gravity extends beyond our home planet. It's the reason planets orbit around stars and galaxies form clusters. It's the reason we see the same side of the moon every night, a phenomenon referred to as tidal locking, caused by the gravitational interaction between the Earth and the moon. And let's not forget about the technologies that rely on our understanding of gravity. Take GPS navigation as an example. The satellites that make GPS possible have to account for the effects of gravity to provide accurate location data. Without understanding gravity, we wouldn't be able to navigate our world as efficiently as we do today. Gravity is even responsible for the tides. The moon's gravitational pull causes the oceans to bulge out in the direction of the moon. When the bulge aligns with the coast, we experience a high tide. When it's out of alignment, we have a low tide. So gravity is constantly at work, shaping our world and our universe. But what has studying gravity taught us? The study of gravity has opened up new frontiers in our understanding of the universe. From the microcosm of atomic particles to the vast expanse of galaxies, gravity's influence is all-encompassing. One of the most intriguing discoveries attributed to the study of gravity is the existence of black holes. These cosmic phenomena are regions of space where gravity is so intense that nothing, not even light, can escape their pull. They're like cosmic vacuum cleaners, sucking in everything that ventures too close. Black holes aren't just fascinating oddities of the universe, they're also crucial to our understanding of physics. They push the boundaries of what we know about gravity, space, and time, challenging us to delve deeper and question further. The study of gravity doesn't just lead us to the outlandish and extraordinary. It also helps us comprehend the structure and evolution of the universe itself. Gravity is the architect of the cosmos. It shapes galaxies, influences the birth and death of stars, and even bends light itself. Gravitational forces determine how galaxies cluster together and form large-scale structures in the universe, giving us a blueprint of the cosmos. Gravity also allows us to peer back in time. By observing gravitational waves, ripples in the fabric of space-time, we can detect cosmic events that occurred billions of years ago. These waves, first predicted by Einstein and later confirmed, provide a new way to observe the universe, complementing traditional light-based astronomy. Moreover, gravity has practical applications in our daily lives. It plays a crucial role in technologies that we take for granted, like GPS navigation. Without a precise understanding of gravity, these systems would fail to provide accurate location data. From the falling apple to the orbiting planet, gravity is the force that binds the universe together. It's a fundamental part of our existence, shaping our understanding of the universe and our place within it. Gravity is more than just a physical phenomenon. It's a window into the universe, a guiding force that leads us to new discoveries and deeper understanding.